Okay, so our next speaker is Daniele Magazzeni, and he's going to talk about opportunistic planning in autonomous underwater missions.
Thank you, Andrew. So this is actually a journal track paper, and it's a work about a robotics project in the context of autonomous underwater missions. And I think this is a good example of how planning and temporal planning in particular can integrate very well into a robotics project and give an important contribution in terms of optimization. So I'll give a context for the project and then I'll focus on the temporal planning part. So this project is about persistent autonomy in underwater robotics, and persistent autonomy means that we have long missions over days or weeks, and ideally we want the AUVs to operate without human intervention. And the kind of tasks that are involved is that given that these installations include manifolds, pipelines, valves in particular, these are the set of tasks that AUVs, so one or more AUVs, have to accomplish. So we have inspecting manifolds and cleaning manifolds and then turning valves, and this is particularly challenging because they are associated to time windows, means that the AUV has to approach the valve panel and turn valves in specific time windows. So there is an interesting temporal synchronization issue here. And of course then you want the AUV to recharge again because they are quite long missions over time. The challenge, an interesting challenge here is that in these long missions there are some opportunities which are called HILPs, meaning high impact, low probability events and opportunities. Again, these are high impact, meaning if you spot one, it's worth exploring and achieving this opportunity, but also low probability events. And in particular, in the underwater domain, this kind of high impact, low probability events are basically spotting chain and following the chain. So here on the left hand side you see a real picture of what the AUV observes when it spots a chain that, as you can see, is not connected to anything in one end. And the problem here is that there are examples where chains are used to anchor large ships, for example, but these chains have just snapped. So you can only spot when this happens when you actually see the ships starting drifting, which is clearly too late. So the point is that when you spot a chain, you really want to follow it in order to check whether it's still linked to the ship or not. On the right hand side there is a ROS visualization tool for underwater missions, and this is what happens when the AUV is following the chain. These are some examples, real examples from some missions where all these numbers here are the numbers of chains that were actually no longer linked to what they were supposed to be linked, and this is clearly an issue. So again, these are low probability in the sense that it's not so frequent that this thing happened, but when they happen you really want to detect them as soon as possible to avoid losing basically the ships. Now the role of planning here is planning with opportunities. So we can see opportunities as soft goals but with high utility. So the hard goals in these missions are completing the task of inspecting structures, while following the chains are not hard goals, but they are soft goals with high utility. However, the problem is that the probability distribution of these chains is not known, so you don't have information about that, and so they cannot be anticipated. As I said, they are high utility, so the point is that if you spot these, it's really better and worth exploring and trying to achieve these opportunities. However, they cannot compromise the hard goals that the mission has to achieve. There is a bunch of related work. In the paper we have a long survey of these. Here I report the ones that I think are more closely related. So there is the work on anticipatory online planning by some of people in the audience, Jay, Wheeler, Min, and the reason why that work cannot be applied is that this work is for opportunities that are very likely to happen. So basically you invest resources in searching for these opportunities, while here the context is where these opportunities are very rare, so you don't want to invest time in advance, but you only want to react when they happen. The second work from Amanda very nice work. Basically, she considers the oversubscripting planning, and however, there the assumption is that you know in advance the locations where you can spot the opportunities, while here you don't. So that's why this cannot be directly applied. And then there is this work on a similar context, but again, there the locations basically where to look were known in advance. So again, the scenario is different because you actually don't know, you have no idea where you can spot the chain. Of course, then there is potentially the possibility of using POM-DPs and conditional planning to deal with this problem. The issue here, however, is that the state space is so huge that POM-DPs approaches really cannot scale, particularly because you have very long horizon mission. Plus, again, you don't have any real information for building the model because you don't have any probability distribution that you can use for building the POM-DP. So the approach we used is temporal planning with end-free time windows. The approach is quite simple. The idea is that we have a distribution for the action durations, and what we do is that when planning we use a conservative approach by using a longer duration, right, than the average, than the mean, and in particular the 95 percentile of the normal distribution there. And what happens is that having overestimated the duration of actions, you end up in possibly saving time. So if this is an example of plan, what happens is that you start executing the action, and because you overestimated the duration, you save time, and this is a window where you can then move the next action in the plan, and so forth and so on. And the idea is that these free windows can be used to fit a plan for achieving an opportunity. So this is how we work. So there is a main plan, and what happens there is that after one action, usually the UV is performing movement and observation, and because of this observation of some structure, it happens to observe also a chain, for example. So as soon as this happens, you want to plan for the opportunity, and when possible, and if possible, to get back to the initial plan in order to accomplish the hard goals for the initial mission. Of course, these opportunities can be iterated, so you can spot an opportunity while trying to accomplish an opportunity. So that's the scheme of it. However, it's really important to make sure that there are enough time and resources to accomplish the opportunity, and then to still be able to achieve the main initial goals, which are the hard goals. So in this particular domain, but this also generalized quite nicely to other domains as well, there are a number of actions that can be subsumed by the action in the main, by the opportunities plan, which are basically the navigation actions. So you can basically skip all the navigation actions in the main plan when taking an opportunity, and do the same movements or reach the same destination using a different path while following the chain. So this is what happened. We have the main plan. We start executing the plan, and after a while we spot the opportunity, and then we have in red are the support action that we can skip. We then execute the opportunistic plan, and we then get back to the original plan. Again, in order to then achieve the initial hard goals. So this is done in PDDL. So planning is not only PDDL, but it's also PDDL. And actually PDDL 2.1 was actually used in deploying the plans in this underwater domain. So this is a bunch of actions. There are more. We mainly use durative actions. Sometimes the duration is fixed. For some other cases, it's the planner in charge of deciding the duration of the action. And this is how to model in PDDL 2.1 the time windows. So here we are saying that the time 400, it's between 400 and 800 is the time window where valves 2 and 3 can be actually operated and turned. And this is an example of plan where you can actually see more or less that, for example, there is turn valve in valve 2 exactly in between the within the time window. These plans were found using POP-F plan, temporal planner. Yes. For let's say using the planning in practice, we use ROSPlan, that in this scenario was responsible on one end from translating the observation made by the sensor into the planning problem, and so then collecting information, creating the planning problem, planning for it, and then dispatching the plan and checking that the execution is fine, and also spotting the opportunities, because what happens is that there is sensor spots the chain to be followed, and this trigger the opportunity for the opportunities into the planning system, into ROS plan. Now, in order to evaluate, so first of all, it worked very well in practice, and this was kind of first real hands evaluation. However, to also provide a kind of theoretical evaluation and qualitative evaluation, clearly one possible comparison is between what we do here in exploiting the opportunity and planning only for the opportunity, to compare this with the fact that as soon as you spot the opportunities, what you can do is just to replan the rest of the mission from scratch, including the hard goals plus the opportunity. This is a very reasonable approach. And actually, replanning also offers something more than what we do with the opportunities, because what you can do is that you can decide how to, for example, exploit and achieve the opportunities later on in the plan, rather than now when I spot the chain, for example. And also the resulting plan can be more efficient because you have a large space for decisions. However, there are two issues. Is that the problem is more difficult to solve because now you have more goals in less time, and the planning time can be longer. And this is crucial for the kind of mission we are interested in, because if there is an opportunity you spot and you want to try to see if you have time for achieving this opportunity, you don't want to spend too much time in thinking if you have time, otherwise you really lose the opportunity, right? And we are talking in terms of seconds needed for quickly making a decision whether to accomplish the opportunity or not. Anyway, in terms of experiments, what we did was to give 10 seconds to the opportunistic approach I just discussed, and up to half an hour for replanning, just to check what happens if we have the opportunity to give to replanning a lot of time. And so there is a big table in the paper. Here I collected the important information. So what we see here are labeled for the experiments, the time needed for the opportunistic plan to solve the opportunity and then to get back to the plan, and then the time needed for the full replanning in finding the first solution, or anyway the better solution within the 30 minutes time. Interestingly, well, on the right hand side you see basically the duration of the overall mission. And interestingly enough, there are only here, these are two cases where the replanned strategy leads to a better plan in terms of duration, because this is what we are interested in, reducing the make span. And in total, in a bunch of experiments, actually the number of times where replanning in half an hour was able to find a better plan is really a tiny portion of the experimental results. Again, I think this is also due to the kind of scenario of domains we are considering. Anyway, it proves that opportunistic planning can work. So in conclusion, I think this is again an example of practical, because that was deployed and executed for real, a practical example of how planning, temporal planning, PDDL planning can integrate into a full robotics project. And opportunistic planning, which is well studied in our community, can be used to deal with opportunistic goals, and in particular high impact, low probability, which in many robotics scenarios is actually something which is quite common. I mean, there are many domains where you can have this kind of high impact, low probability events. And we think that this approach is a good trade-off between planning time and planning efficiency. Again, because replanning from scratch would lead to better plan only if you give a lot of time. While if you don't have a lot of time, this approach can provide you with a good trade-off. That's it. Thank you.
All right. Any questions? Anyone? Yeah.
Okay. When you basically find an opportunity, you skip some original. The original action are optional. So
are optional, you said?
Yes. If you can skip them, it means that in the original plan you have some activities you can skip.
Okay.
Are optional. So why this?
Okay, that's a good question. First of all, you cannot skip all actions.
Okay.
You can only skip the navigation actions. In this sense, they are not that they're optional. They are the best path the planner found for the initial goals without the opportunities. Okay? So when you spot the opportunities, you can say, I will move, so the navigation is towards different waypoints and then back to the general plan. But of course, you cannot skip action like turn valves.
Okay.
Right? So what we call the support action, which is what you can skip, are the navigation actions. Okay? You can also actually skip the observations as long as you are able, the planner is able to reschedule these observation tasks later on in the plan. But all the action linked to the time windows, they cannot be skipped, otherwise you miss those windows.
Okay.
Thanks.
I was curious, when you replan for an opportunity, which is exactly the goal, and when do you consider the goal achieved? If you have to follow the chain, I mean, unless you don't know how long the chain is, you don't know how long it will take to reach this goal, and what do you do then?
That's a very good question. I think I missed to say this. I think it depends on the domain. In the underwater domain, what you have is that you have a number of repetitive observations to state that you did find the chain. Because it's also possible that what you spotted is not actually a chain, right? So, for example, in this scenario, there are 5 repetitive observations of the chain that is a proof in this domain that you actually did spot the chain. This becomes the information to report back. So in this case, the goal is to have this kind of repetitive observation.
And what happens when and if you realize that you cannot achieve the goal before the hard goals is achieved?
In that case, you just give up, you don't go for the opportunity. This is exactly what the planner has to realize. If there is time, enough time to get back, you take the opportunity. Otherwise, you just say I can't, and you
start it and you break it.
You don't even start. So the planner checks. If there is no time, keep going with the initial plan.
Thank you.
But you don't know how long the chain is, so you don't know how long out of the way you're going to be going.
Yeah, but the point is to report that there is a chain that for a successful observation.
You just need to make 5 observations.
Exactly. To notify that there can be a problem. Yeah.
You're not going to drive kilometers out of the way.
No, you can't. Otherwise, again, you miss the hard goals you are tasked with at the beginning.
I'm just curious about what you do with the ROS plan, because you said now that you also use it for discovering opportunities.
Yeah.
In other talks, it seems that you use it for dispatching and executing. So
yeah, you can use.
How
no, thanks. You can use.
Functionalities are hidden inside.
Yes, you can use ROS plan exactly for both things, because what we have, I don't know if the picture show this, but ROS plan contains contains a knowledge base which is dynamically updated by the sensors that you have in your robots in the underwaters. What happens is that any information that the sensor detect are stored into the knowledge base which is inside the ROS plan, and every time translated into the planning problem. So ROS plan on one end helps you to create the PDDL model, meaning domain and problem file, and then to dispatch. So we use both. Does this answer your question?
So essentially it covers the functional, what is commonly used in robotics is at the functional level.
Yeah.
Okay.
Exploiting, I mean, all the functionality in ROS, because in ROS you have messages for what the sensor detects, and this is automatically translated into PDDL. And thanks to this work, we actually implemented the libraries for AUVs. So now you can use ROS plan with AUVs scenarios.
Okay, but it's time to see you again.
Thank you.